any of us that do research, and particularly experimental research, have some options in deciding what kind of research we're going to have. And in the olden days, the sort of the default method was just to purchase it. And so if you buy off-the-shelf hardware, it's going to cost usually quite a bit of money for scientific hardware, and it's very difficult to customize it. The other option that we've had is you could make it yourself, and that usually doesn't cost as much, but it does take a lot of time. Or you could pay someone to customize and make it very detailed. And so this is an example of a dual beam photoconductivity apparatus, and you can see it's kludged together with a whole big bunch of equipment, and it took years to build. It took a lot of money, but it was able to get some new and interesting results. And this is the old way. You could either spend a lot of your time or a huge amount of money in order to be able to get a custom scientific tool in order to do an exploration that hadn't been done before. Luckily today we've got open hardware, and that's the new way. And this is the ability to get low-cost hardware that's still top of the line and custom for your scientific needs. So to give you a little bit of background on open source, the idea of open source hardware for science comes from the free and open source software movement, where people would share code and allow people the freedom to use it in any way they want. So you can download it, copy it, study it, change it, improve it, but it had a viral sort of share-alike portion to the license, which means that if you do make an improvement on the software code, you're entitled to share it back with the community. And so this underlies everything from Android to Wikipedia to basically every major internet website that you've ever used and a lot of the software makers. That idea of open source software has now moved over to open source hardware. And a good example for that is the Arduino. This is a microcontroller that allows you to take information from the environment and then act on that environment. And in the olden days, learning how to program a microcontroller was very difficult. In order to be able to do even something simple like keep a cup of coffee warm was a complex task. And now with the Arduino, because it's open source, and not only have the code and the schematics and the designs and everything is freely available, but there's huge libraries that have been built up with many types of sensors and actuators so that it's very easy to automate processes, including those of running scientific hardware. These microcontrollers are relatively inexpensive, and there's an enormous community in the open source hardware community that supports it. So for example, you can use a simple Arduino as an oscilloscope, and this isn't the best oscilloscope ever in the world, but it's functional to the point that it's useful in most labs for most reasons that you need an oscilloscope. You can use the same Arduino as a pH meter, and again, this isn't necessarily the best pH meter ever, but it's a pretty good one, and you're using a shield, which is an electronic component that fits on top of the Arduino in order to give it increased functionality. If you can take a look at pH, it's possible to also use the Arduino as a data logger. So you can do, say, pH and oxidation reduction potential and temperature. You can use the same Arduino brain to run an open PCR, which is a system to replicate DNA for $600. And so you can see that the open source hardware community has been building upon itself using this basic microcontroller at the foundation to make some relatively complex systems. One of the most impressive of the complex systems that's been developed from Arduino to date is self-replicating rapid prototyper, or RepRap. If you've heard of 3D printing in the news, it's probably because of this project. This was started at Bath University by the professor on the left, who used a additive manufacturing machine to make the parts to build the first RepRap, which were then used to fabricate the parts to build the second RepRap, and so forth and so on. RepRaps at this point operate using fused filament fabrication. So a kind of a long stream of spaghetti is pushed down through a hot zone that moves over top of a bed that lays down a fraction of a millimeter of plastic one layer at a time. Using this very simple process, it's basically just a hot glue gun that shoots plastic, you can make very sophisticated scientific tools. To give you an idea of how powerful this is and why I got interested in it, my research group used to primarily focus on solar photovoltaics. One of the projects we were working on was the one laptop per child, which was a $100 computer meant for the developing world. And unfortunately, like all computers, it needed electricity, and for many of the places it was being targeted, they just simply didn't have it. And so our students were working on solar powering those laptops. And I was very excited because I finally had access to a rapid prototyper, and I had them do it. And in the case, just to hold the solar cells, not just made out of plastic, was $65, which was almost as much as the whole computer and much more expensive than the solar panels and the small battery. And so the patent system that we're sort of used to in the conventional side truly failed additive manufacturing. 3D printing and additive manufacturing go back to the 1980s. Basically, no one had access to it. Even the concept, the fused deposition modeling, was trademarked. No one was allowed to use it other than Stratasys that had those original patents. Then there was very little technological evolution over those 20 years. The least expensive FDM system you could buy on the market was $20,000. You compare that to the RepRap community today, which has fused filament fabrication that anyone can use in terms of a term. There's weekly improvements, RepRaps that cost well under $1,000. There's dozens of companies competing instead of one. In the patent system, you had proprietary feedstock. We can use any feedstock, including waste plastic. My solar test case only cost $5 using commercial plastic and less than $1 using recycled plastic. So these are some of my students working on kind of the first version of RepRap in my lab. Then this is the second version. You can see it's getting better. These evolutionary steps that the technology has taken didn't just happen in my lab. It happened in hundreds of labs and hundreds of garages and people's basements all over the world. And as each new improvement happened, it was shared with the rest of us, and so it got better and better. By the time we got to version 3 is when I started to see as a scientist this could be truly useful. So we weren't just making, cases for consumer products like a solar-powered laptop. This picture shows some very interesting things. First of all, the computer was discarded from my university as waste because it was running Windows. We stripped Windows off, put on open source Linux, and OpenSCAD, which is a script-based open source CAD package that can do very complicated things. It just so happened that in my lab, the automated filter wheel changer broke right at the beginning of the summer. It was going to cost $2,500 to replace and take 5 months to actually get it in stock. And anybody that does research, you know that in the summer that's our most productive times, and this was basically going to shut me out on my most productive time on my most heavily used automated tool. And so I hired a high school student to use this discarded computer, free software, to make our lab a parametric filter wheel changer, one that's better than everything else on the market. It was run by an Arduino. It was used a 3D printer that you can see here, kind of a third generation. It's getting faster and easier to build and smaller and just better really in every technical way that you can think of. And so we were able to build that filter wheel changer for $50. And again, it was better than everything that was available on the market. It was exactly what I needed for my lab, and that just hadn't existed before. And so for me, this is when the light bulb really went off that I could use this to do some really hardcore tools of this process by kind of leveraging the capabilities that have come before me from the people that had worked on the Arduino and then the people that had worked in the RepRap. And so this is kind of version 4 of our RepRap, and you can see that the design is completely changed. And this came from a German that developed a Delta system, which is often used for pick-and-place robots in the electronics industry, and applied that to a 3D printer. What's interesting about this is for the last one, it took several days, like basically a week to build version 3. Version 4 can be built in a day by somebody that knows what they're doing for less than $500 in parts. And again, it's faster, higher resolution, better technically in every way than the 3D printers of the past, even the proprietary, very expensive ones. And so we built a class around it. This is the first class. This is a completely open source 3D printing class. They only use open source hardware and software. The class is available online, so anyone that wants to take it or take any of the modules from it, that they're free to do that. And both the class and the overall RepRap community have continued to improve its functionalities. And so one of the things you can do with the basic Delta design is to turn it into a stage robot. And that stage robot can then use a fixed head. Like on the left, we're using a syringe in order to be able to do syringe printing. On the right, we're using it to do PCB milling. And if you compare the micrographs there of sort of a milled by us and milled by a professional PCB outlet, you can see that the professional system is better. There's not quite as much wobble in their lines, but our system is plenty good enough in order to be able to make electronics for most of the things that most of us have functional in our labs. And so now this 3D printer is being used to manufacture the electronics, including boards that go on top of the Arduino in order to give us even more functionality. And so once you have sort of caught this bug where you're no longer going to be satisfied just to buy the scientific equipment that's available on the shelf, but be able to hack it and move it forward, whether or not you do that yourself or whether you pay someone else to do it or join one of these open source hardware groups, this is the way forward. And so I wrote the book, The Open Source Lab, which goes step by step in how to do all this stuff, including operate RepRaps or other fused filament 3D printers in order to be able to make scientific tools, and the same with the electronics. And so the way this works is that this cartoon kind of summarizes it, where the first scientist put some effort together into making a small little tube for her samples. And she's already put the work in, and she did it for herself. And the extra effort that she has to do to share it is really trivial. So she shares her design, and it goes up on the web. And because the design is good already, other scientists can take it, and that will save them a little bit of time to do the other things they want to do. So whether it's a test tube rack or some sort of little mini centrifuge. And so then these scientists use her design to build theirs, which is more complicated, and then they're obligated to reshare it. So they share it on the web as well. And now the original scientist, who just did a little bit of sharing, now has very high-tech tools available at her disposal because of her sharing. And so the trick that where she can benefit from sharing is by putting on that open source license so that other people are obligated to reshare with her, and she can print it out and go. And so this happened in real life, where the simple designs for this little tube became very complex. And so here's a bunch of examples of open source centrifuges. On the left is the Dremelfuge, which is just a chuck that can be attached to a standard Dremel in order to be able to make an ultra-centrifuge. There's a completely 3D printable centrifuge in the middle, and then some electronic ones on the right. These are more than adequate to solve most of the centrifuging needs in many labs. The same with test tube racks. And so again, starting off very simple with something just to hold test tubes, but then you can make magnetic racks, which can cost hundreds of dollars for literally just a few dollars. So you spend like $1 printing out the piece in plastic, you order some magnets from Amazon for like $5, and suddenly you've made yourself a several $100 test tube rack. These magnetic test tube racks, if you just make 2 or 3, you've suddenly paid for the price of your 3D printer, and you've justified all of its uses. These 3D printers can't only print kind of normal everyday plastics like ABS. They can also print more advanced plastics like polypropylene, which then can be used in chemical experiments in the clean room for things like custom wafer dippers, things that can save you reagents and make it safer for your students and yourself to work in the labs. Here's some examples of pipette racks, but also the pipette men themselves. And so again, this is starting to save on the orders of hundreds and sometimes even thousands of dollars for standard lab equipment that is now available to everyone. Custom ultrasonic cleaning jigs for basically any process that you can imagine, again, are easily made. Adjustable ultrasonic clamps, and so this is showing an example of using 3D printing to utilize a material that you couldn't otherwise 3D print. And so you can also 3D print molds that you can then pour in your molding material in order to provide whatever mechanical, electrical, magnetic properties that you might need. One of the really nice things that came out of the RepRap community was this idea that they would make as much of their developmental work parametric. And so they began using OpenSCAD, which is a script-based CAD package. And this shows you the script and the resultant 3D design for a parametric shadow band. So a shadow band is used for pyranometer for outdoor solar test research, and basically all it does is shadow the path of the sun. These cost normally hundreds of dollars, but they're very, very simple physically. And so what this code allows people to do is to change these variables up at the top in order to make a shadow band for their particular piece of equipment in their particular location. And so this code solves everybody's shadow band problems for the rest of time and allows them to replicate this technology digitally wherever they happen to be. In order to make it even easier, there's customizer apps that go on top of that OpenSCAD code that make it really, really easy in order for people that might be intimidated by the code in order to customize designs for scientific tools and then be able to fabricate them, whether with a laser cutter or a mill or a 3D printer. And so really leveraging this idea of digital distributed manufacturing in order for one person to make the design and then all the rest of us to benefit from it. My group that does solar cell research, a lot of what we do is actually optics related. And so we created an open source optics library of customizable 3D printable optics, mechanical optics equipment. And then we looked at the cost. And so we were doing things like lens holders and mirror holders and chopper wheels, lab jacks, things that all of us use in our labs all the time. Only, let's say, like a typical lens holder might cost $25 to $50, and we can print one out for like a quarter and use like a nickel or two of nuts and bolts in order to be able to get the same thing. Just as an example, optical rail usually runs on the order of $380 a meter. Open beam costs $12 a meter and is just as good for the vast majority of applications. And so overall,